Let's look at OpenStack's College Physics Chapter 2 Problem 27. In a slapshot, a hockey player accelerates the puck from a velocity of 8 meters per second to 40 meters per second in the same direction. If this takes 3.33 times 10 to the negative 2 seconds, calculate the distance over which the puck accelerates. So we have to organize our knowns and unknowns. The first thing we know is that the puck accelerates from an initial velocity of 8 meters per second. So I will write V initial is 8 meters per second to 40 meters per second. So V final is 40 meters per second, and I should use sig figs. So let me get rid of that. So it's 40.0 meters per second. In the same direction. So I'm going to already draw the diagram. Here is the puck, and this is the initial velocity. Later on, the puck has a larger velocity, so this is V final. And that means that the puck was being accelerated. So this is the acceleration of the puck, so that the initial velocity is less than the final velocity. All right, the next thing we know is that it takes an amount of time of 3.33 times 10 to the negative 2 seconds to accelerate the puck from an initial velocity to the final velocity. And we're looking for the distance over which the puck accelerates. So we want a delta x. All right, so I drew my diagram, and since I picked V initial and V final to be in this direction, I'm going to call this my positive x. And I see that all of these quantities are positive because they all point in the same direction as the positive x direction. So now I need to solve for delta x, and I'm going to look at my equations and see which equations have a delta x in them. So I noticed that both the second and third equation have the delta x, have the x in it, but they also all have the acceleration. I don't know the acceleration, so before I can choose an equation to solve for the delta x, I first have to solve for the acceleration. So the simplest one to use here is this first equation, because I know the initial velocity, I know the final velocity, and I know the time. So using this equation, I can solve for the acceleration. So let's do that first. So I'm going to copy the equation over. V final is V initial plus AT, and I will solve for the acceleration. So that will be V final minus V initial divided by T. So when I plug in the numbers, the acceleration will become V final, so that is 40.0 meters per second, minus the initial velocity, so that's 8.00 meters per second, divided by time, that's 3.33 times 10 to the negative 2 seconds. If I plug in the numbers for the acceleration, I get 9.61 times 10 to the second meters per second squared. So now I have the acceleration. I know the acceleration from here, and I can plug it into this equation or that equation and solve for the delta x. So I can use either one of these two equations. I'm going to start with this one. Maybe I'll use the other one if I have room on my paper here. So V final squared equals V initial squared plus 2a delta x, which means that delta x is going to be V final squared minus V initial squared divided by 2a. So V final squared, that is 40.0 meters per second quantity squared, minus V initial squared, so that is 8.00 meters per second quantity squared. Don't be tempted to subtract 8 from 40 and then square it, because it's not the same as 40 squared minus 8 squared. All right, so divided by 2 times the acceleration. So the acceleration was 9.61 times 10 to the second meters per second squared. So when we plug in those numbers, we end up with delta x being equal to 0.799 meters. All right, how about we use the other equation? So we have x final equals x initial plus v initial t plus 1/2 a t squared. And what I'm looking for is the delta x. So delta x is x final minus x initial, and that will be v initial t plus 1/2 a t squared. So delta x is 8 meters per second times the time, which is 3.33 times 10 to the negative 2 seconds, plus 1/2 times the acceleration, which we found to be 9.61 times 10 to the second meters per second squared, times time squared. So that is 3.33 times 10 to the negative 2 seconds quantity squared. And guess what? If I plug in all those numbers, I end up with delta x as 0.799 meters. So this is an excellent thing. I was able to compare the solution for one with a solution for the other by using the different equations, and I got the same answer.